This is Chapter 6. So Chapter 7 we sort of already covered. So you'll see the Chapter 7 binary in the last set. You could actually do that right now. You can actually do the Chapter 5 ones. You could actually do all of them, because even the Chapter 8 ones are sort of self-explanatory. So, yeah, in fact, these levels are much less of a cognitive load.
Oh, cool. That's not very true.
Really?
Yeah, some of them.
Oh, Chapter 7 might be a cognitive load, but definitely the Chapter 8 ones they're more fun.
Well, the one is with the PS command.
The PS command. There's learning PS commands, and then the other one is learning signals, which I haven't taught you yet, but those levels were designed by students who knew how to design levels.
Went through this
versus me. I was like, I think they should know this. So, all right, we're going to start Chapter 6, which is the memory hierarchy. So up until now, we have talked about memory and this uniform, this illusion of having a uniform address space for each process, this virtual memory abstraction, where a process believes that it has the entire range of memory from 0 to all Fs for x86-64. And the reason why we give them this abstraction is that it allows you to easily multitask between processes, and they don't have to worry about what addresses other processes are using. The other thing that this does is it hides the underlying memory organization. Your program doesn't have to worry about how those bits are actually stored by the processor. It's all hidden. Okay?
Which means, more importantly, they can't.
They can't. If you're a bad guy looking for someone else's bits in the cloud, for example, then you don't want that exposed. So that's correct. Okay. So when we talk about storing data in memory, we typically talk about random access memory. And this is memory that's used, non-persistent memory, used to store your code and your data. There are two kinds of RAM. There's static RAM and there's dynamic RAM. Static RAM is the faster, more expensive RAM. So the way this RAM is built is with 6 transistors for each bit. And it's continually kept powered. And as long as the power stays active on the SRAM, the value is retained. Okay. Dynamic RAM is cheaper, much higher in terms of capacity typically. And the way it's implemented is with each bit in memory is a single capacitor. It's basically a battery, and a transistor to either charge it or discharge it. So the value in dynamic RAM, unlike the static RAM, has to be refreshed every 10 to 100 milliseconds. So you turn the gate on, you charge up that capacitor, but unless you go back and refresh that charge, it's just like any battery. It'll start leaking the charge, and then you'll lose your bit. So dynamic RAM has to be refreshed periodically, and the fact that it's not powered, it doesn't have the 6 transistor layout, it's actually slower to read a bit off of that battery. Basically, it's reading a bit off of a battery.
Way cheaper.
It's way cheaper, but it's way slower too. Okay. So, one of the things that happened in the last 20 years is that the speed between the CPU and the rest of memory has gotten wider. So all the way on the left is 1985, and if you look at the cycle times of static memory, dynamic memory, and CPU, they're all pretty much the same, right? So this is why you have x86 as a register-poor architecture, right? Because memory is as fast as your CPU speed. So I don't need a lot of registers, right? I can go straight to memory for all of my data.
This is also an interesting consequence of why we have algorithms are like clocked in O time big O notation. And the reason big O notation disregards memory access is because when big O notation was designed, memory access was just as fast as the CPU. So to simplify everything, you can get an extremely accurate measurement on architecture by just only counting actions and not thinking about memory.
Okay. So I would argue that big O notation should take into account, that's just a constant factor, your memory speed. So it would just make this, it would make the factor larger, but the larger order, so you guys haven't taken algorithms yet, so that does, this conversation won't make sense.
Yeah, big O notation for asymptotic behavior. But we use it only for asymptotic behavior, but back then they used it for like actual performance as well, because you accurately could, and now we can't really.
Right. Okay, so one of the things that you'll see is that the access time of static memory and dynamic memory, this is the number of nanoseconds that it takes to read something from these memories. They've declined significantly, with static memory giving you from 150 to about 1.3 nanoseconds. So this is a factor of 115 times improvement in the last 30-odd years. Similarly, with dynamic memory, you go from 200 to 20. This is a factor of 10. So you see right here, the amount of improvement is an order of magnitude different between static memory and dynamic. When you get to the CPU, it goes from a cycle time of 166 nanoseconds all the way down now to 0.33. So this improvement is a 500 times improvement. So this is the disparity now between the speed of the CPU and the speed of the memory subsystem. This is what's driving Intel to put a whole bunch of cache memories close to the CPU, just because of this disparity. One of the things you'll notice is that at around 2000, the cycle times have sort of peaked. So memory's getting a little bit of a chance to catch up, but still, this disparity is so great that we're going to have these issues with memory speed for a while.
So why the cycle time has increased? I mean, if you see there it peaks and now it's
they've gone to a lower duty cycle, so this power wall. Basically, if you're running it faster and faster, the amount of power that you're generating off of that,
it just gives you so much heat that you literally melt the CPU.
Yeah.
So
like it's like,
like
per square inch, it's like a nuclear power reactor, like that density.
Wow.
It's on that order of magnitude, yes.
You also
so
have
they're just
issues.
nuking it with more and more power and more energy, heat and everything. They're just like, why not we do more every cycle? So that's when they started really like pumping all those optimizations and a bunch of stuff. So like, for every cycle, they want to average 1.5 to 3 actions. And that's how you get a CPU that's 2 gigahertz but faster than a Pentium 4 at 4 to 5 gigahertz.
So wouldn't that impact the memory? Like if you're doing so much more with your CPU at a single time and your memory hasn't improved as much, then actually you're making things worse kind of. Right?
Yeah, so you have to do things like wider data paths, right? Especially for if you're doing like an AVX 512. Well, I better be able to get like the entire cache line in parallel. For example, like I have to make a wide data path in order to consume
data.
To consume that thing. Yeah. All right, so I didn't want to get to the details of all this, but more to just point out the fact that there is this huge disparity, and that in order to fix this or to address this disparity, we basically design our current systems to get these really small, fast SRAM-based memories close to the CPU. And then the cheaper, slower dynamic memory is typically kept further away. So we've organized our memory in a hierarchy in order to try and feed the CPU with enough data. And that's basically what it is. Specifically, the way the memory hierarchy is organized is that we have hierarchy levels in there where, for example, level K has the faster, smaller memory device, and that will basically serve as a cache for level K plus 1, which has a larger, slower device. And that's what we're going to look at in this class, in this lecture. Okay. So the idea is that you would want to keep your frequently used stuff in level K, and then go to level K plus 1 for the infrequent stuff. The key to all of this is that it's managed automatically in hardware. But you, as a programmer, have influence as to how the hardware is able to help you. So that's why we're covering it, because it's not just some magic that the caching system knows how to get the best memory performance out of your program. You, as a programmer, have to mindfully program your stuff to take advantage of what's underneath. This is what it looks like. At the top of the hierarchy are your processor registers, your RAX, RBX, and those sorts of things. And then from there, you have basically levels of cache, where we label these as L1, 2, 3, 4, and 5. And as you go down the hierarchy, you get into slower forms of storage. You go from on-chip caches, per-core on-chip caches, to unified core on-chip caches, to shared on-chip caches, to off-chip main memory. Those are the things you put in your motherboard. Those are the dynamic RAM. And then if that's not enough memory for your process, then you can swap out to secondary storage, your disk. And if that's not enough, you can actually use a network. Okay, go over the network to store your memory for your process. This is different than file system sort of access. Yeah.
We use on chip, you're actually talking about
on the CPU. Yeah. Okay. So if you organize your memory in a hierarchy, the thing that you are implicitly relying upon is locality. So if I put something in level K, I should definitely be using that piece of data in the future. Otherwise, it makes no sense. Okay, so there's two kinds of locality. There's temporal locality, where an item that you recently used is likely to be used again. So that's what this picture is, where this item in red will get reused in the future with high probability. And then there's spatial locality. Spatial locality says if I'm using this particular memory location on the left, I will almost immediately use the data next to it. So two kinds of locality that you can take advantage of. And this is what your caches and your memory hierarchy is hoping that you do. Okay, so here is a program, and I want you to identify these kinds of locality in code. And so what I have here are examples of spatial locality and temporal locality for both data access and instruction access. So what I first want, given this code, give me an example of spatial locality for data access. Just shout it out.
Oh, we're not doing that.
Yeah, the next one will be
It's just the array itself, right?
the array itself. So because you are sequencing through A of 0, then 1, then 2, then 3, that's spatial locality for data access. Okay. Give an example of temporal locality for data access. The sum. You're continually updating this same data location. I works too. You're continually updating I. Yeah, I should put that in
And
there.
you're consistently talking about int too, so you're having an access, right? So that access is still part of temporal, like you still have to deal with that locality, right?
N is a constant, and we saw in that loop
Oh,
multi
that's
thing.
right.
Well, if it is a constant. If it's not a constant, then you're right.
Yeah, I was assuming most general, so it wouldn't be a constant.
Yeah, then it would be, well, it's the difference between, it's locality. It's the difference between whether it's data locality or code locality, right? Because it's actually built into the, yeah. Yeah, because it's like the immediate is like, no, actually it would be, no, you would be comparing to that constant. Okay, yeah. All right, give an example of spatial locality for instruction access. For instruction access.
Oh, or comparison and increment.
Comparison and increment would be one. So basically, all of the instructions that implement this logic are probably stored in a row. And in fact, you've seen this. When you reverse engineer a loop, It's not like one instruction is, over there and one instruction is over there. That would make it really hard to disassemble.
Well, it is, though, because the comparison's always at the bottom, right before the jump, and normally you're setting it right beginning.
Yeah, I guess relatively speaking. At least it's not 1 kilobyte away. Yeah.
That's what you're talking about.
All right, so they're mostly in the same location. So that would be spatial locality. Give an example of temporal locality for instruction access.
Plus equals.
The plus equals, because that gets hit every single loop iteration. So you're
Plus
going
plus.
anything in the loop would give you temporal locality for instruction access, because you're hitting all those probably four instructions over and over again. All right. Okay, so given what you know about arrays, which of the two functions has better locality, the top or the bottom? And explain why, if you give an answer.
I couldn't tell you why, but my interest is in the top one.
Yes.
I would say that it's the top. And the reason I would say that is because you say int I first, and then you have the first for loop, and you have int j, and you have second for loop. But then you could also argue that the second one has a better because it's nested, so you go ij and then ji.
They're both nested.
I mean, like, declare int I, and then int j, and then you reference int j, then you reference int I.
This is not that. This is something.
The top one is better spatial locality because you remember from the 2D array levels, the ij is really equal to I plus 1, 0, 0. So what you're doing is you're looping I all the way around each time. So you're just accessing memory sequentially, and then when you get to the next part of the loop, you're just going to the I plus 1, 0 part.
Yes. So 2D arrays are stored in row major order. So the elements of each row are stored sequentially. So when you have a loop counter, j, and this is the thing that's going to be changing the most frequently, it should be the case that j is the column because this allows all of the elements in this row to be stored to be accessed sequentially. If you do something like this, what you're doing is instead of varying the column the most, you're varying the row the most. And so you're striping down the rows of your matrix, and you're basically hopping over lines of memory locations.
But does that mean that one of them is faster than the other? Or this
Yeah,
just...
one of them's faster. Which one is? The top one? Yeah,
How
for sure.
significant would it be?
Well, it's
Pretty significant. You can quantify this. We'll be able to quantify this at the end of this class, exactly how significant the improvement will be. Your memory performance makes a huge difference. And we'll figure out the number of cycles, because if you're continually missing in your L1 cache, well, the penalty from L1 to L2 is about a dozen cycles, I believe. It's like 3 cycles to get to L1 and 12 to get to L2.
So it could be like 4 times increase.
Could be. Yep. Could
If
be.
you have a cast miss, aren't you losing 500,000 2 million cycles?
Depends on where you're missing in the hierarchy. Yeah.
So the top one's faster because it takes less cycles to get that memory, or is it...
Yes, it gets better locality in terms
so
of
it's not because that was implemented in assembly, it's actually
the way you're accessing memory.
Okay.
Is going to be better for a cache. And this is not obvious yet why it's better, but we'll see, because the way the caches work.
And the compiler won't edit this out, right?
It will not. Typically, will
because
not.
it wouldn't know if it mattered where it was going first.
Actually, I don't know. Maybe someone could do this. Do it with O3 and see if it actually will flip it. Maybe because then it would know. I mean, it might have everything it has to be able to say that's equivalent. For this particular loop, I think it actually might be able to automatically do that.
Is there ever an edge case where you have 2 rows separated by a physical boundary? where you'd be able to parallel two different memory accesses at the same time on two different rows?
Not that I know of. Not explicitly that I know of.
Okay.
No. Okay, here's practice problem 6-7. Permute the loops so that the function scans the 3D array A with a stride 1 reference pattern and thus has good spatial locality. Given what we know about how these arrays are stored, change the ordering of these loops. There's some scrap paper up here.
It's on your door, guys. Come over.
Thing is happy. So this is the permutation Kij. The last index grows the fastest, followed by the next fastest, I, followed by K. All right. Here's another one. Practice problem 6-8. Rank order the functions with respect to the spatial locality enjoyed by each. So here you have a struct that has a 3-dimensional velocity and a 3-dimensional acceleration for a particular point. And if you recall, in a struct, these two are structs are stored contiguously. And within this struct, you have the velocity vector stored contiguously, followed by the acceleration vector stored contiguously. And say you are going to clear all of the elements, all of the points in this array. There are 3 routines here that do this. So, for example, in the top, you have a pointer to an array of points here. And for all of the elements from 0 to n, and then for so this is going through each point, 0 to n, that's what the I is. And then for for j from 0 to 3, this is going to zero out the velocity vector for this point. That's what this line does. And then this one zeroes out the acceleration vector for this point. And then similarly, clear 2 and clear 3. Clear 2 does the same thing for each point. For j is equal to 0, j less than 3, it clears out velocity and acceleration all in a single for loop. So rather than using 2 separate for loops, it uses 1 for loop. And then clear 3 says for every point, or for every dimension 0 to 3, I'm going to go through every point and zero out the velocity vector of each point, and then zero out the acceleration vector for each point. So 3 ways of zeroing out the exact same data structure, but they have different locality. So which one has the best? Yes?
2, 1, 3.
2, 1, 3. You see, you say 2 has the best, and then 1, and then 3? All right. Well, that's one guess. I'll wait for 2 more guesses. I'll wait for 2 more guesses. So 2, 1, 3 is a suggestion. Yes. What is 1, 2, 3 is a suggestion? Do we have a second on any of these? Which one do you want?
Okay. So if I say 3, 2, 1, then we should have like only 1 or 2 left before we have it exhaustively guessed.
Math majors.
3, 1, 2.
You're not a math major, are you? You're guessing what? 3, 1, 2.
Well, there's only 6 permutations.
Yeah. All right. That one's the best one. So why is that one the best one?
Because essentially, as you're going through your array, you have your array of pointers, right, or your array of structs, and then you also inside of that have each little tiny little array that you have for the velocity and acceleration that it's going through before it moves on to the next. So it's, if you're looking at it, it could load up each individual velocity array and then each individual acceleration array, and then it could also load all of these structs all at the same time and be the fastest. Like if you're looking at like the things that it can load in. Right? Does that make sense? Or is that completely
Almost. So yeah, what you want to do, so this is stored contiguously, right?
Yeah.
So you want to completely finish a point before you go to the next point. So this immediately eliminates this one at the bottom, right? This is going and saying, oh, I'm going to do this by dimension of the velocity and the acceleration. And then I'm going to cross over all the different points. And then for the next dimension, I'm going to cross over all the points again. That's the worst. Then these two both cycle through points, like it takes a point first. So it sequences through the points in the outer. But then on the inner, the top one is going to say, I'm going to take all of the velocity vectors first and zero those out. And then I'm going to go to the acceleration vectors. These are stored contiguously. So this is exactly going straight through the strut and zeroing it out in memory ordering. Whereas the one in the middle, yes, it saves you from this extra for loop. But what it's going to do is it's going to hop back and forth between the velocity vector and the acceleration vector, zeroing it out. So technically, this is, I mean, it's okay, but it's not as sequential as that one is. Right? So the outer loop on this, you got the right point, but then through the, say it's the x dimension gets zeroed out first between the velocity and the acceleration, then the y dimension, then the z dimension. So it's hopping back and forth between the two arrays. All right. Okay, so we've referred to this sort of in the abstract. The way these hierarchies are built is through caches. And so here we have a picture of a cache where this is the smaller, faster, more expensive memory. And because it's smaller, it can only contain a subset of the blocks in your larger memory store. So in this case, we number the blocks in memory from 0 to wherever, up to 15 in this case. And then when we want to access a piece, say we want to access a block, we will look into the cache. Say I want block 4. We'll first look into the cache, see if block 4 is there. And if block 4 isn't there, then I will not do that. I will bring it up and replace an entry in the cache. Yeah.
Does that mean that every single cache has a complete visual, complete mirror of every smaller cache above it? So that means every
Yes.
space?
This has a complete copy of that. But if the
No, it should be. That makes sense.
Yes.
I was just trying to make sure that I understood.
So yeah, and you'll notice that every one of these blocks is resident in memory. There's a copy of it in memory. But one of the things is if you're updating this block all the time, whether or not that gets pushed out immediately to memory is cache dependent, implementation dependent. But that is correct. Typically, there's a mapping between the block in the cache and its actual memory location in the K+1 store. All right, so if you want block 4 is not there, so you bring it in and you replace, for example, block 8. Then if you want block 10 isn't in there, so you bring that up and you replace, say, block 14. And then if you have an access for either block 4, 9, 10, or 3, then you'll hit in the cache, and then you won't have to go to this slower memory. And so the name of the game is to always try and hit in this cache in order to keep the CPU happy, or well fed. Okay. So when we talk about caches, there are 3 different reasons why you would miss in the cache. The first reason is a compulsory miss. And this is when you first start up your process, you have nothing in the cache, right? It's completely blank. And these cold misses are mandatory. So they happen when the program starts up. They also happen when you're context switching. So if one process has ownership of the CPU and all of a sudden has been told to swap out for another process, the cache for that process has to be completely invalidated. Because then you have another process with a different memory map, with a different set of memory locations and values being brought in. So you typically invalidate everything in the cache. Yeah.
So does that mean that if you have multiple CPUs running different programs, rely on the same memory space, does that mean it has to be kept at a further down the list cache, making it harder for it to actually get access to that and change it because it has to have interdependence?
We'll talk about coherency next class, next lecture. Yeah. Okay. Another kind of miss is a conflict miss. So most caches will limit where a block can be placed to specific locations. So in this case, in the previous slide, I didn't tell you this, but it shows that a block at level k plus 1 is placed in block I mod 4 at level k. And I'm going to show you this. So this is basically saying the blocks in memory 0, 4, 8, and 2 get placed at I mod 4, which is block 0 in the cache. So all of these blocks in this column are going to get mapped into this block. All of the blocks in this column will get mapped into this particular block location, and etc. So this is one way of mapping your underlying memory locations into the cache. And that's typically, this is a pretty common mapping. But the issue is that what happens if I have a referencing pattern of 080808 in this previous slide? Yeah, I keep switching them out. So 100% miss if I have that access pattern. That's called a conflict miss, where because I have accesses that are conflicting into this cache location, I'll get 100% missing. So that's another way you can get misses in caches. The last one is a capacity miss. And this occurs if you're sequencing through an array multiple times, and that array doesn't fit into a cache. Right? So say I have 1,000 integers, and I'm repeatedly going through the 1,000 integers and updating them. If my cache can't store the 1,000 integers, then basically I will completely overflow that cache, and I'll miss every single time I access data in it. Okay, so those are the three kinds of caches. And the name of the game when we design a cache is to minimize the bottom two. This one, there's not much you can do about it. You have to basically do it by sizing, but we can definitely minimize a conflict. Okay. So now I'm going to talk about a general cache organization. This was a very specific one that I showed you. But the general way to organize caches is through what we basically define S number of sets in our cache. So in the previous slide, this was pictured as 4 sets. So there were 4 specific sets that our caches could belong into. That's what I'm referring to in this slide as the number of sets. And then for each set, I can have a certain number of blocks in each set. Now in the previous picture, there was only 1. But there are caches that will allow you to do multiple blocks per set. And then finally, in each block, I can store any number of bytes. So in terms of the actual data. So that is abstractly what we're going to look at in this lecture. Okay. In terms of what is stored at each one of these blocks, typically you have your data. So based on the number of bytes per block, you have 0 to b minus 1. You also have a unique identifier. Because this cache is storing memory locations from all over your memory space, when you want to get access to data in this cache, you have to know that it's the exact block that you're looking for. So there is this unique identifier, this tag, that's associated with the blocks that you're storing, and that allows you to identify this. And then there's a valid bit. So the valid bit tells you whether or not the data that's there is legitimate. And so if you are context switching from one process to another, the way the processor clears the cache is to reset the valid bit to 0 on everything in the cache all at once. It's not going to go and overwrite any of the data in there. It's just going to clear the valid bit. Okay, so if we have this as our cache organization, then the size of this cache is going to be the number of sets that you have times the number of blocks in each set, which is E, times the number of bytes in a block, which is B. So capacity in bytes is S times E times B. That's something that you should just memorize, because that's basically what we're going to use from here on out. Okay. You want a picture? Did you get it? Okay. All right, so that is our cache organization. As it turns out, when we apply an address to memory, we need to figure out a way of indexing our cache to see if our data is there. And the way we do it is based on the address of the memory that we're looking for. And so typically, we use parts of the address to determine which set we're going to look for our block in, and which block offset in the block, which piece of data in that block that we're looking for. And then parts of the address will also be used as a tag to uniquely identify the data that's in the cache. So if we have capital S number of sets, then the number of address bits that we need to map this address into a set is log base 2 of capital S. So if we have 8 sets in our cache, and we're going to use the bits of an address to determine which of those 8 we're going to belong to, we need 3 bits. 3 bits in S to do so. Likewise, if the size of one of our blocks is, for example, 16 bytes, then to index which byte in that block we're looking for, we need log base 2 of the number of bytes in that block, which would be 4 in this case. So if I have 16 bytes per block, I would need 4 bits to say which byte out of that 16 do I want. So this is the structure of how I am going to look up my information in the cache. I'm going to use S as the set bits and then B as the byte offset bits. And then the rest of this address is going to be used as a tag to uniquely identify the data. Okay. So, and the reason why we're doing this is because the cache is storing a subset of blocks, and the only way we can determine if that block is actually ours is to make sure that the rest of our address, our T bits, uniquely identifies it. Okay. So in order to determine the size of your tag, we have to be given the number of bytes in main memory, and so the address of our word, the length of this address is basically the log base 2 of the total size of main memory. So, for example, if we have a 64-bit architecture, it can address 2 to the 64 addresses. And so the tag bit, the number of bits in that address is 64, and then the total size of memory is 2 to the n. So we use this little m as the number of address bits in the address. And then the tag is going to consist of the bits that aren't used between the set bits and the block offset. So everything that's not used to index the set and to index the byte in the block, everything else is going to be used as the tag. And this will be, when I actually show you an example of how this all works, it'll hopefully make more sense.
Does that mean you can only address only 2 to the 48 different addresses? So for a 64-bit architecture, so you notice this is a huge address. And so most machines don't have 2 to the 64 sort of size memory banks. And so it's often the case in 64-bit x86 that there's only 48 bits really being used. The address is a large block of the address, 24 bits. That's right, 2 to the 64
is so massive that really a whole bunch of the address space is not used. So you only store 48 bits in the tag. I put that there just in case people sort of as extra information. Okay,
So this is the way, given an address, this is the way a cache is addressed to find the data associated with this address. So the first thing that happens is that you locate the set that this address belongs to, and you're going to use these S bits as a set index to identify which of these 2 to the S sets that your data belongs to. And then what you're going to do is you're going to check to see if any one of these blocks in this set has a block that matches your tag. Because any number of blocks could have been placed in this cache. You are looking for a very specific block that exactly matches your tag. And then if you do find one that matches your tag, then the rest of the bits will tell you which byte in this block to return. All right. So that is functionally how a cache is going to work. Yeah. Is that good, or do you have questions?
No, I was just looking at it for a minute. So if it's only using 48 of the bits, does that create a potential for mismatch or collision?
In terms of between
If you're using the 48 bits of
the
tag?
the loader and the operating system know not to allocate out of the. It knows that those address bits
So
are
the-
being
the
unused.
OS
Has been notified.
those are dancing.
Yes, yes. Those bits are pretty much ignored as part of the address.
So it only works if your OS works with it.
Yes.
How is it actually accessing that stuff so fast? Wouldn't it have to have a massive set of XOR gates?
This is all done in parallel, right? Obviously, electrically. In fact, we'll talk about the matching and this sort of stuff. Yeah. You would need parallel circuitry to do the. Yeah, this isn't Google where you're indexing and creating tables. This is all done as parallel matches against every single block
In logic.
for that in logic. Yeah.
Yeah.
So
Like,
you're
that's
literally
crazy.
comparing multiple different things at once.
Yes. In the circuitry to do that is well known. It's just a little bit of extra hardware.
But you're doing it in a bunch of different circuits, not just one.
Yeah, in parallel circuits. Yeah. This is not the sequential searching that you might think of when you're like, oh, I'm going to search linearly through my cache. That's not how it works underneath. And we'll show that.
Oh, does it use the valid bit and then if it
That's
matches-
part of the logic. This is a big comparator is part of the logic, and you would need parallel comparators. Yeah, and then it would just basically you apply this address onto this cache, and it'll immediately tell you hit, miss, and then the data associated with it. This is being done linearly just to show you sort of what's involved in doing a cache lookup. Okay.
How much of this is on our final?
There's a great practice final that I would point you to see what is actually the kinds of questions I would ask about this.
Great as in awesome or great as in big in size?
Or great as in the
Real
big
dry.
cry.
Grade as in representative of what you might get on what you will get on the final.
That's not very great.
No. All right. So, for example, I should be able to ask you something like this now. This table gives you the parameters of a number of different caches. The cache and the block size, so C and B, are given in bytes. For each cache, derive the missing values. And then this is the formula for you. This is what I told you to remember on the previous slide. Your cache size in bytes is the number of sets in your cache, the number of blocks in your set, and the number of bytes in your block. Okay. So here we have the first one, and I can walk through the first one. Cache number 1 has 32 address bits. The size of the cache is 1,024 bytes. The number of bytes in a block is 4, and then the number of lines in a set is 1. Find the number of sets. So if the cache is 1,024, the sets are unknown. E is 1,
and B is 4, well then the number of sets is 1024 divided by 4.
256.
It's 256.
Calculator on the final.
No. This is easy math. This is easy math, right?
Unless you're
Yeah, this is playing that 2048 game a bunch. And then,
unless you're dyslexic.
yeah.
This is just bit shifting. You can
And,
binary
yeah.
shifting, right?
This is a skill I would like you to just bake. Like, yeah. Most people do this in their head eventually, the powers of 2. So I don't want to hamstring you with a calculator on that. All right, so in order to have, if you have 256 sets, in order to index that number of sets, then the number of bits you need to index that is log base 2 of 256, which is 8. So you need 8 bits out of the address to say which set do I look for my data in. And then because the number of bytes in a block is 4, I need 2 bits to say which byte am I looking for in the block that gets returned. The number of tag bits, which is at the end, is basically m minus the bits used for the set and the block offset. So this is 32 minus 10, which is 22. Okay, so let me have you do the next 2.
Where do we get B from again?
What's that?
I missed where we got B from. 2.
Because you have 4 bytes in a block,
Right.
in order to identify which byte you want out of that, you would need 2 bits. Because you have the 00 byte, the 01 byte, the 10 byte, and the 11 byte. Those are the 4 bytes. The little m is the number of bits in your address. So I have to give that to you in order to get you the number of bits in the tag. So one of the shortcuts for memorizing your powers of 2, I should probably give you this if I'm not allowing calculators. The first thing you need to know is that this 1024 is 2 to the 10th. So that's a good thing to know. And then 32 is 2 to the 5th. 256 is 2 to the 8th. So if you know your bit positions, you can memorize just certain signposts. Because then, like, 128 is 2 to the 7th. 64 is 2 to the 6th. These sorts of things. And then when you do your multiplication, for example, B times E is 2 to the 5th times 2 to the 5th. That's 2 to the 10th. So 32 times 32 is 1024. So this is probably a shortcut that I'm using now automatically, which probably you guys should start. I think that's an easier way of looking at this problem.
Juggle powers, yeah.
Yeah, to juggle powers, yeah. And then this is 2 to the 8th. That should be well known in terms of that's the byte. 255 values. That should definitely be known. Okay. So in this case, the number of sets. So you take 1024, and then you divide it by 8 times 4. So here is 2 to the 5th right here. So this is 2 to the 3rd, 2 squared. So this is 32, or 2 to the 5th. And if you divide 2 to the 10th by 2 to the 5th, you subtract the exponents, and you're left with 32 as what's left over. So 32 sets based on this formula for cache size. Log base 2 of that is the number of set bits that you use. Because the number of bytes in a block is 8 bytes, you need 3 bits to address the bytes in the block. So that's why log base 2 of 8 is 3. The number of set bits plus the number of block offset bits is 8. So the number of tag bits is 32 minus 8, which is 24. The last one, the number of sets is 1, right? Because the number of blocks
the number of bytes per block and the number of blocks in a set will multiply. Well, when you multiply those together, you actually get the capacity of the cache itself. That means there can only be a single set. And when there's only a single set, there are no address bits, right? Because you're looking at the same place for everything, is basically what's happening. But you still have log base 2 of 32 in terms of the number of bits in the block offset. So then the tag is going to be the number of block offset bits, 32 minus the number of block offset bits, which is 27. Okay. This is sort of dry, but we're going to get to cache simulation soon. And then this stuff will make, the point of this will be hopefully a little bit clearer. The last one is you taking a memory mountain program and running it on a bunch of systems just to see how you can pull out cache performance numbers off of different CPUs. I'd be interested in your CPU. Yours has probably got a well-endowed cache. So you're probably, like, when you run that program, run it on Linux Lab, run it on the latest and greatest hardware that you have, if you have latest and my hardware is 2 years old. So.
What about really old, or like a little F0?
Yeah, run it on if you have a Raspberry Pi, then you can compile it on there. Yeah, the C code, it's just regular portable C code. Yeah, do it on a Raspberry Pi and see, like, can I infer the cache parameters on that? So that's basically what you're doing.
Assignment 4 is easier than assignment 3.
Assignment 4 is just you running this program and looking at the results and trying to figure out whether or not your cache program is giving you what you know is on that CPU. Yeah, there's no programming.
How's that work under emulation?
Emulation depends on if you're emulating. Depends on how you're emulating. If you're emulating the CPU, very poorly. If you're running virtualized and then these instructions are hitting the actual hardware, it should be fine. You should get the same. Okay. Okay, practice problem 611. Consider the following code that runs on a system with a cache of the form 512 sets, 1 block per set, 32 bytes per block. So where this block size is given in bytes, so there's 32 bytes in a block, there's 512 sets. You have this array where you're going to accumulate the elements of this array onto this sum. The first thing I want you to answer is how many integers can fit into a single block, given what you know about this array and the block size. So 8, right? So 32 bytes. Each one of these ints is 4 bytes. So 8 integers can be stored on a single line.
So does that mean it actually behooves you to create like arrays that are in mod of your cache?
You can create them on any dimension, but when you work with them, you want to work with them mod your cache size. Your working set, they call it, we'll get to this later, your working set size should hopefully fit into the cache, is the idea. Okay. Assuming sequential allocation of this integer array, what is the maximum number of integers from the array that can be stored in this cache at any point in time? Close. 4,096. So you've played 2048 probably a lot, right?
No.
No,
but
but
I don't know. I've been doing that for 30 years. So
Okay.
That'd be for longs.
What's it?
That'd be for longs.
Okay. So yeah, 8 times 512, this is 4,096. Because you have 512 sets, and each set's got one line in it, and that line has got 32 bytes, or 8 integers. So it's just 8 times 512. So now you know if you have this integer array of 4096, this will all fit into cache. Well, assuming no one else is there polluting your cache. But yeah, you can get that an array of 4096 integers into that cache.
So when you say line, does that relate in any way to like engineering lines, like data paths, or is it just like copied straight from the?
They call it a cache line because visually they're picking off. Yeah, they organize caches in lines of rows of data, and they say I'm going to just bring in that whole line of data.
Oh, so it's like a line of text, not like
a line of bytes. Yeah. That's where a line comes from.
I was always confused.
Yeah.
What they were talking about.
Yeah, that's what it is. Okay. Okay, so now we're going to talk about the types of caches. Based on the general organization that we just went through, we saw the direct map cache as the very first cache, where you have one block per set. So here are 4 sets, 1 block per set. And then each location in memory, each column, for example, maps into a single location in the cache. So in this case, E is 1. And the size of the cache is basically the number of sets times the number of bytes in each block. Okay, S times B. So this is what it looks like. You're going to have your sets on the left, and each one has a single block. And in this case, we'll even make the number of bytes in a block to be 1 byte. So each one of these is 1 byte. This is the degenerate cache. This is the simplest cache you can implement. And then what we have is the address. We have the least significant bits. Because there's only 1 byte in this block, you have 0 byte bits. And then the rightmost bits are simply your set. So here is your set bits are at the end. So when you do a cache lookup on this simple cache, you figure out what set you're looking for. And then based on the block that is there at that set, you then compare the tag. And if the tag matches and the valid bit is 1, then you can use the byte that gets returned. So if the tag doesn't match, then you have to go to the next level of the caching hierarchy and bring back the block that you need. Yeah.
Does it load that byte both into your memory and also into the cache at the same time?
Into your memory. It loads it into the register. So if you are requesting it and trying to put it into a register, it'll put it both in the cache and in the register. That's what it is. Yes.
So is your cache watching, is it just as the data goes through, it passes through the cache and the cache retains it?
Yes. It stores a copy of the thing that you just got out of main memory. And then I would imagine you're taking that memory and putting it in a register or sending it to the ALU.
About this in the circuitry.
Yeah. Well, sometimes it doesn't hit the register. If it can go straight to the arithmetic unit if it's being consumed that way. And we saw the execution path had the loads and the stores from the bottom, and then the ALU was up there. It could actually just go straight in there rather than to the register file, especially if it's a memory operand that's being used as part of an arithmetic instruction. Then it could be consumed directly by the ALU.
So is the cache serial in the path, or is it
Which path?
the path from memory to the place where you're storing it, whether it's registered?
I'm going to guess parallel, just because when you have the circuitry there, it makes no sense to not feed it both places where it needs to go. I'm assuming so. But I'm not really a hardware guy, so I guess. Any ECE students here that taking architecture?
Oh, no.
Oh, all right. Okay, so here is the cache that we're going to look at for the rest of our examples. Our main memory is 16 bytes. It's got 16 addresses, so it's a 4-bit processor.
All zeros is the beginning address. All ones is the highest. Here we have a cache for this main memory. It's got 4 sets. So set 0, 0, set 0, 1, set 1, 0, and set 1, 1. In each set, there is a single block, and in this block, there's 1 byte. So this is the trivial cache again. If we have 4 bits in our address space, then the number of set bits has to be log base 2 of 4, because we have 4 sets. So 2 bits for the number of bits in S. The number of bits for B is 0 because there's only a single byte in this cache, or in this line. That means the rest of the bits, the other 2 bits, are the tag bit. So this is the way we're going to index this cache. We're going to use the least significant 2 bits as the index, and then the most significant 2 bits as the tag. And we're going to look at this access pattern. We're going to go 0, 3, 8, 3, 8. And we're going to look at what the cache does as we access this. So the first thing is 0, 0, 0, 0. What we'll do is we'll figure out which set to look at. So the set that we're looking at is the 0, 0 set. And then we're going to see if there's any data there that can be returned. And it turns out this is not valid. So let's say the valid bit hasn't been set. This is going to be a cache miss. And what gets brought in is the data at 0, 0, 0, 0, which is hex 0, 0. So we'll fill in the data with that. And then we have to store the tag that uniquely associates this data with that address. And so the tag is binary 0, 0. This is hexadecimal 0, 0, and this is binary 0, 0, just to differentiate the two. Basically, yeah, these memory addresses are labeled with their associated address. So this is a cache miss. 0, 0, 1, 1, what this is going to do is your set number is 1, 1, and this is going to miss. And it's going to bring in hex 33, and the tag is going to be 0, 0 to uniquely identify that block or that byte. The next access is 1, 0, 0, 0. The set is going to be 0, 0, which is going to be up to here. But if you look at the tag is 1, 0, and because this tag is 0, 0 and not 1, 0, this is going to be a miss. And this is why you need the tag to make sure that the data that's in that cache is actually yours. In this case, it's not. So the tag doesn't match. So this is also a cache miss. And then it's going to evict this data and bring in what's at 1, 0, 0, 0, which is hex 88, and then it's going to update the tag to 1, 0. The next access is 0, 0, 1, 1. So the set is 1, 1. The tag is 0, 0. You have a match. So this is your cache hit. And then in the last one, your set is 0, 0. Your tag is 1, 0. So you get another hit. So this is your cache miss rate. 3 misses out of 5 total accesses, so a miss rate of 60%. Okay.
What is the average miss rate?
Oh, it's workload dependent. It goes all over the place.
So it can be anywhere from like 0.01% to like 99.
Yes. Yeah, you could pathologically miss on every single, if you wanted to. You could write a program. Actually, that would be a great program to have you guys write. Write a program that pathologically misses in the cache.
You should do that.
Using the smallest number of bytes.
If we write that as a capture the flag.
Then you have to.
That would be. What's
You
it?
have to assume that the field architecture is going to mess around and optimize all of our cache misses out for you.
Yeah.
And current architecture is really, really good at that.
All right. That might show up in a. Yeah. Well, you guys have enough program. Well, yeah. We'll see. All right. So identify issue number 1. Here is your access pattern. 0, 0, 0, 0, then 1, then 2, then 3, then 4, then 5. What is the miss rate on this?
A lot.
A
A lot. Put a number on it, though.
100%.
100%. Yeah, because they're all different. You're sequentially accessing it, and so you will fill up, you'll miss on 0 through 3. And then when you get to 4, you'll be back up here, and then you'll miss again. 100% miss rate. And we said, hey, I thought, locality, spatial locality, how come I'm not getting anything? Shouldn't I improve performance on sequentially accessing it? What were those previous practice problems all about if I can't get improvement doing spatial locality? So here's the thing about block size. This thing is always missing because the block size is 1 byte. So in order to leverage spatial locality, you need larger block sizes. And by that, it means that if I get byte 0, then I will also retrieve bytes 1 through 15. And then I will store that all in the same line so that they can all be accessed as hits after that initial miss. Right? Now, this cache line phenomenon is the other reason why we were aligning structs. Right? If you remember that, I don't want my long word to be half on one cache line and half on the other one. I want that thing to be aligned so like it just gets all brought in on a single cache line. So there's where that comes from.
Yeah.
Okay.
All right.
That was a good lightning bolt from heaven.
So the idea of block sizes is to load all the data from nearby address, and in particular, the addresses like if you're doing sequential accesses, the ones that you're about to access is basically what the cache line is doing. Okay. All right, and we saw this before. When you have a block size of capital B, then the number of bits that you'll need to address the individual bytes in that block will be little b, which is log base 2 of the number of bytes. Okay, so here is a direct map cache with a block size of 8. So now we have 8 bytes here. And because we have 8 bytes here, we now have 3 bits of a block offset. And then the next bits are used for the set index as we had before. So what we do is we use these middle bits for the set index. Then what we do is we look for the tag to match. And then if it does do a hit, then the block offset, in this case it's 100, this will be used to identify which bytes to return out of that line. And in this case, we're assuming that maybe we're fetching an integer. So it returns the 4 bytes that are there. Okay, so here is another direct map cache. It has 2 sets, 0 and 1, but it has 2 bytes per block. Okay, so here is an access pattern, 0001, 1011. What is the hit rate or miss rate of this access pattern? One in every 3 does what? 1 in every 3 misses? Almost. Miss hit. Yeah, is that what? Yeah, 50%. So this is what happens. The first one is a miss. Now here you have a set index, which is a single bit, and a block offset, which is a single bit, right? So you have just 2 sets. So one bit to figure out which set you're at, and then 1 bit to determine whether or not you want the low byte or the high byte. So here, when you get this address 0, the set that it's going to look at is set 0. Nothing's going to be there, so what you're going to do is you're going to bring the byte in from this memory location, and you're going to bring in a line of memory. You're going to bring both of these bytes in. So you're going to bring in 00 and 01 into memory.
And then when you go to 0001, it's going to go back into this cache, and it's going to hit because the tag matches. The 00 of this address matches the tag, but you want the other byte. So this will be a hit. It'll return that byte. When you go to 0010, this is going to go to set number 1, and that's blank, so you're going to miss. But then you're going to bring in both 22 and 33 together so that your next access will hit. So this is what you're doing with the spatial locality. You're actually getting a subsequent hit after the initial miss, because rather than bringing in just a single byte, you decided to bring in multiple bytes into your cache line. This is where you finally get benefits from spatial locality. Okay. Practice problem, and we'll be using this cache later, which is why I'm giving this to you. Consider the following cache. It's got 2 sets. It's got 1 block per set. It's got 4 bytes per block, and it's using 5 address bits. Derive the values for the number of address bits used for the tag, the set, and the block offset. So that same diagram as before. And then draw a diagram of the cache after you do that. So the number of bits in the block offset, log base 2 of capital B, so 2 bits. The number of bits in the set index is log base 2
Of 2, which is 1.
which is of 2, which is 1. And then the number of bits in the tag is the total number of bits in the address, M, which is 5, minus the number of bits in the set and the number of bits in the block offset, which would be 2. And this is what it would look like. 2 tag bits, followed by a set bit, followed by 2 bits for the block offset. And then this is what the cache looks like. You have 2 sets. S is equal to 0, S is equal to 1. And then within the set, your block has 4 bytes. Capital B is 4. And then 2 bits of tag to figure out whether or not you have the right block in there.
So you still do have the index.
Yeah, you have the index because you have multiple sets. Okay.
Are they always sorted this way?
They are always sorted in this order, yes. Yeah.
Is that just by convention, or is there
By function, because if you had the byte offsets in the middle and the set index at the end, then you're basically spraying sequential. It doesn't make logical sense to have the byte offset as the index of your byte array. That means your sequential addresses would be sprayed all over different parts of memory, basically. That's what if you reorganize it the other way. But yeah, it's always done in this order because the least significant bits have to be, it's sort of like storing an array in row major order. The least significant bits have to be the addresses that are contiguously incrementing have to be stored in the same sort of location. So if they're sprayed across sets, then your like sequential addresses are sprayed all over the cache is basically the issue with that. Okay, so consider this cache. We're going to derive a miss rate for the following access pattern, and I'll walk through this with you. So the first one obviously is going to be a miss, but when it misses, which addresses will it bring in? The first, second, third, and fourth. So it'll go from 0 to 3 on the miss. So the data from all 0 to 00011, that's all brought in. And then this next access, hit or miss. That's a hit. And then the next access will also be a hit. There's your spatial locality. Then you do 00100. This is a miss because this is the set is 1 and set 1 was empty. And so you set the tag to 00. This is a miss. This gets data from 00100 to 00111, the next 4 bytes. And then when you do 00111, well, you had already brought that in on this cache line, so that's going to be a hit. And likewise, you can show yourself that you get this access pattern. Yeah.
And part of the access pattern is because of how you're calling it too.
Sequentially.
It's all sequential.
Yeah.
Well,
Mostly.
yeah.
Except for the last one here.
The last.
And you'll notice the last one is in fact a miss because you had already replaced it over. Yeah, over here. These two, this one replaced it, and then this one replaced that one, and then so that's why that misses. Okay, issue number 2. So we're back again with 4 sets. One line per set, and then 1 byte per line. This access pattern, 262626. Miss rate is 100%. Which set is it gonna hit? Yeah, it's gonna hit the 10 set. So in this case, you have 4 sets. So the last 2 bits are the set index because the number of bytes in the block is 1. So this is both. These addresses are basically going to thrash the cache by going to the 10 set of the cache. So it's basically going to conflict. These 2 data accesses will continually conflict with this block. So, which is a problem because if this is your only access pattern, that means this cache location, and this cache location are completely unused, while this one is getting thrashed. So, yeah.
Is this why only certain types of or only certain parts of memory can be mapped to an individual location in here? Is because when you're accessing each set, you can only access part of the. You're only gonna have 2 bits to go into there.
So the reason why we're organizing our cache like this is because we don't want to do a full-on search of our cache for our block, right? So we're using these bits to say, okay, I'm going to narrow the search down to this line. And then I'll do a parallel search, or this set of lines, and I'll do a parallel search on those. That's basically what we're doing here. So a certain number of the address bits are going to narrow down where in the cache to look, and then I can do the lookup more efficiently. That's basically what's going on. There are these fully associative memories, which will do a parallel compare. There's parallel compare circuitry on every memory location, and then you can say, give me something that matches this content, and then it'll return. So that's associative memory. If you're a computer architecture person, that's what that is.
There's also this concept that people are developing in parallel, which is, I think they call it smart memory, or computative memory, or whatever. It's like similar to associative memory, but basically the memory registers are also slightly intelligent, and it can do very simple computations. So
yeah, so they started, here's a model of computation where put the small bits of computation near the memory, right?
Rather than the other way around.
Yeah, so there is that, and so that's basically what the content addressable memory is. Basically that you're putting this huge comparator over there, and then you're doing some processing with a lookup.
So you can do all the easier stuff right immediately in memory before you put it off to CPU.
Right. So.
Doesn't that have problems with like?
Oh, it's got lots of problems. Yeah.
Okay. I was like, that sounds like corruption.
Yeah,
Sounds like thread safety
CPU versus
issues,
memory.
not to mention all this
The reality is that
Yeah, actually,
if this one CPU puts out 300 watts of heat, you can't do that.
but these crazier models of computation, this is what folks like, I don't know if you guys know Ivan Sutherland. He's got this asynchronous research lab upstairs. He's a Turing Award winner, and he's working on asynchronous chips, which gets rid of this model of computation for something potentially faster that's not clocked. Because when you get a chip that's this big for Intel, it's hard to synchronize all your operations and clock them. So that's what his research project is about. And then you would put computation all over, and then you would just send it in a pipeline to the different places that need it, and you wouldn't clock it. You would just wait for it to come back.
So you would have a CPU with actually no clock speed?
Yeah, well, you could. The self-clocking, basically. So, in fact, Galois down the road does a self-clocking encryption chip that's asynchronous. And I was just talking to this guy. He's like, "Yeah, I could pour liquid nitrogen on it to speed it up, and then power it in a way that makes it go faster, as long as I cool it. Or if I don't have liquid nitrogen, I can completely slow it down for low power. That's what this model of computation will allow you to do.
That's
Yeah, so that's the. You were there at Galois. Yeah, I was talking to that guy. Whoa.
Was that Chris or was that?
That was Joe.
That was Joe.
Can I buy one of these things?
Well, the government wants these things. Yeah. Well, they wouldn't say it was the NSA, but the government, the Department of Defense wanted it. Okay. So here is the issue. When you have direct map caches, you get these conflict misses. So 0808, here it was 2626. So each memory address belonging to exactly one block in the cache will cause you to basically thrash in the cache. Okay. So this will lead you to what we call set associative caches. So rather than each set storing a single block, you can have it store multiple blocks. And this will reduce what we call conflict misses. The larger your set is, and the larger the associativity of that set, the fewer cache conflicts there are. And then you can improve the hit rate in your cache. But there is an issue here, is that it doesn't come free. Because what I just mentioned before, this parallel compare, has to be implemented. Your cache, if it has like 16 different lines in its set, then your cache has to do a parallel compare of 16 things. Because you don't want your cache to be searching, right? This is not a linear searching algorithm. This has to be done in one cycle. Like, you don't want your cache lookup to take more than one cycle. So all of this stuff, all of this comparison has to be done in parallel in one cycle, which is hard, can be prohibitive cost-wise.
Wouldn't this mean the chip would be a lot bigger, or the cache at least would be a lot bigger, and would that draw more power?
Exactly. Yep. Yes. Bigger. You got more logic gates rather than memory. And so the silicon that you're using for the comparators, well, what happens if I use more memory? What happens if I made my cache bigger instead of increasing the associativity? Maybe that would have been a better approach than blowing up the associativity. So this is where your cache design, like the Intel engineers have to say, let me see what normal workloads are or what common workloads are and try and figure out if I can size my cache to help the most people. And so that's that's where the engineering comes in when you're designing a cache. Okay, I think I'm going to, let me see if I can, I'm going to stop there.